The universe is filled with countless stars, each with its own story. But have you ever wondered about the life cycle of these celestial objects? Join us on a journey through the fascinating stages that shape the life of a star. Stars are born within vast clouds of gas and dust called nebulae. These stellar nurseries provide the materials necessary for star formation. Over time, the force of gravity causes these clouds to collapse under their own weight, initiating the birth of a star. As the collapse of the nebula progresses, the protostar at the core continues to grow, fueled by the relentless force of gravity. Matter from the surrounding disk of gas and dust spirals inward, gradually accreting onto the protostar. This accumulation of matter fuels the growth of the protostar, causing it to increase in size and temperature. As more and more matter falls onto the protostar, it undergoes a remarkable transformation. The intense gravitational pressure and the rising temperatures trigger the onset of nuclear fusion within its core. At this pivotal moment, the protostar transitions into a true star, marking the beginning of its life as a shining celestial entity. The process of nuclear fusion in the star's core is a fundamental and awe-inspiring phenomenon. Within the seething hot core, hydrogen atoms are subjected to extreme pressures and temperatures. Through the process of fusion, hydrogen atoms combine to form helium, releasing an incredible amount of energy in the process. This energy, in the form of light and heat, radiates outward, illuminating the surrounding space and providing the star with its luminosity. As the protostar transitions into a fully formed star, it enters a phase known as the main sequence. During this phase, the star achieves a state of equilibrium between the inward gravitational force and the outward pressure generated by nuclear fusion. This delicate balance sustains the star's stability, allowing it to shine steadily for millions or even billions of years. For smaller stars like our Sun, the gradual depletion of hydrogen fuel marks a significant turning point in their evolution. As the hydrogen in the core diminishes, the balance between gravitational collapse and fusion energy production becomes disrupted. The core begins to contract under its own weight, while the outer layers of the star expand, causing the star to undergo a remarkable transformation. As the core contracts, it grows denser and hotter, initiating the fusion of helium atoms into heavier elements like carbon and oxygen. While the core experiences this contraction and fusion activity, the outer layers of the star respond by expanding outward. The star's outer envelope swells, and it takes on a vibrant reddish hue. This new phase is known as the red giant stage. During the red giant phase, the star becomes significantly larger than its previous size. In fact, a red giant can expand to many times its original diameter, engulfing planets and other celestial bodies that were once in its vicinity. The star's outer layers extend far beyond their previous boundaries, and its luminosity increases as well. The expansion of the star's outer layers leads to important consequences. The increased surface area of the star allows it to radiate energy more efficiently, resulting in a substantial increase in brightness. The reddish color of a red giant is indicative of its lower surface temperature compared to its earlier stages, but its overall brightness compensates for this apparent cooling. During this phase, red giants often exhibit pulsations and irregularities in their size and luminosity. These pulsations are caused by complex internal processes within the star, including convective motions and interactions between different layers. As a result, the star may undergo periodic variations in its brightness and size, creating a mesmerizing cosmic spectacle. For a red giant star like our Sun, this phase is the prelude to its final stages. Eventually, the red giant will shed its outer layers, releasing a stunning display of stellar fireworks, called a planetary nebula. The ejected layers form intricate patterns and shapes as they disperse into space, leaving behind a remnant core known as a white dwarf. The white dwarf is composed mainly of carbon and oxygen, tightly packed together with the weight of the star's entire mass. Although incredibly hot, often reaching temperatures of tens of thousands of degrees Celsius, the white dwarf no longer sustains nuclear fusion reactions. Without the energy-producing process of fusion, the white dwarf begins its slow journey toward its ultimate fate. Over an astronomical timescale, spanning billions of years, the white dwarf gradually cools down. The star's intense heat dissipates into space and its luminosity diminishes. As the white dwarf loses its thermal energy, it transitions from a dazzling beacon to a fading ember. The cooling process of a white dwarf is a consequence of its limited energy reservoir. With no new fuel being produced and no fusion reactions occurring, the white dwarf relies solely on the residual heat left over from its earlier stages. This gradual dissipation of heat is primarily due to the emission of thermal radiation into space. As time passes, the white dwarf's surface temperature decreases further, causing it to emit radiation at longer wavelengths. Initially shining as a brilliant white-hot object, the white dwarf's glow shifts toward the red end of the spectrum, signifying its cooling state. Eventually, the white dwarf's surface temperature becomes so low that it can no longer emit visible light, rendering it nearly invisible. When a white dwarf finally reaches a state of complete cooling, it becomes what is known as a black dwarf. A black dwarf is essentially a stellar remnant, a cold and dark object floating silently through space. As of our current understanding of the universe, it is believed that no black dwarfs currently exist, as the time required for a white dwarf to cool to this extent is longer than the age of the universe itself. But for stars much more massive than the Sun, the journey is different. When these behemoths exhaust their nuclear fuel, the core collapses under its own gravity, resulting in a supernova. The supernova explosion scatters the outer layers into space, leaving behind an incredibly dense core called a neutron star. Neutron stars are incredibly compact, spinning rapidly and emitting beams of radiation. In rare cases, when the collapsing core of a massive star is even more massive, the gravitational pull becomes so strong that it forms a black hole. Black holes have such intense gravity that nothing, not even light, can escape their grasp. From their births to their ultimate destinies, stars paint the tapestry of our universe. Each star's life cycle adds to the richness and diversity of our cosmic neighborhood, reminding us of the vastness and wonder that lies beyond our planet. Thanks for watching, and I will see you in the next video.